All right, so today we're starting talking about electron organization. And so we've talked a lot about the structure of atoms. We've talked a lot about the nucleus, which contains the protons and the neutrons. And we've talked about the fact that the electrons are kind of around the nucleus. So they're not in the nucleus, they kind of go around the nucleus in some way or another. But we haven't really talked about where exactly they are or how we talk about where electrons are. And so that's what we're going to start doing today, is discussing the way electrons move, how we describe where electrons are, and then the models of the atom that are important when thinking about what the electrons are doing. And there's these two models down here, and we'll talk more about these two models as we go through these slides today. But let's start off talking about something called the Heisenberg uncertainty principle. And that's the very first thing in your notes. And the Heisenberg uncertainty principle, it's named after a scientist named Heisenberg. And basically what it says is that it's impossible for us to measure electrons exactly. It's impossible for us to measure both the location, meaning where the electron is, so location. It's impossible to know both the location and the velocity of an electron at the same time. So we can't know both of those things simultaneously. We can only ever know where the electron is or how fast it's moving. It's impossible for us to know both these things. And so you might already imagine that there's some uncertainty involved with where electrons are and describing what they're doing. And so that's the first thing to note when we're talking about all this electron stuff, is that a lot of the answer is we really don't know. All we can do is predict what electrons are doing and where they are. And so that's what we're talking about, is making a reasonable prediction for what the electrons are doing. So as we do in science, we like to come up with models for things. And scientists have come up with lots of different models of the atom. But there are two in particular that are important for explaining how electrons are organized. The first one is called the planetary model. Planetary model, or we more commonly hear it called the Bohr model. Oh, and I guess I'm repeating the word model. So the Bohr, or the planetary model, is developed by Niels Bohr, and this is the Bohr model. It's the one we've been drawing, where we put the nucleus in the middle of the atom, and then we put the electrons on rings, otherwise called energy levels, around the atom. So the electrons go on the energy levels, or the rings, and then the nucleus is in the middle. And this model is super useful because it shows how electrons are, moving around the nucleus, and it shows that electrons are in different energy states. So there are some electrons in that ground state. There's some electrons in the first energy level, some electrons in the second energy level, and some electrons in the third energy level, maybe, or fourth or fifth or sixth. And it also helps us show the movement of electrons between the energy states. We talked about with the flame test that electrons were starting out in the ground state. We stick them in the fire, they gain some energy, they bump up into that excited state, and then eventually they have to give off that energy and go back into the ground state. And so the Bohr model is super convenient for helping us show that. So maybe we have an electron starting out in the ground state right here. It gains some energy, it jumps up to a higher energy level, and then eventually it falls back down to the ground state energy level. So this is a great model for showing the different energies of electrons. So we like the planetary, or the Bohr model, for that. What this model is not particularly good at doing is showing the actual location of electrons, because electrons move really, really fast and pretty randomly. And so they're not really going to stay on these nice, clean, circular orbits. They don't really move like the planets do around the sun. In reality, they are more moving at random. And so we have a different model of the atom that shows areas where electrons are likely to be. And this model is developed by Erwin Schrödinger, and so it's often called the cloud model. Cloud model, or the other name for it is the quantum mechanical model. Quantum mechanical. Sorry, my writing is not so great there. The cloud or the quantum mechanical model of the atom. It shows us where electrons are likely to be. So it's not saying that these areas are full of electrons. It's just saying that a certain electron is likely to be in this space, and a certain electron is likely to be in this space or this space, and so on and so forth. And this model is based in probability. So it's not saying that there are electrons filling those spaces. It's just saying that electrons are likely to be in these spaces. Probability. Sorry, my handwriting's not so great. So those are two very important models of the atom that help us to understand what electrons are doing, how they're moving, and where they are. Does anyone have any questions about this before we move on to the next slide? All right, we're going to move on to the next slide. But once again, you can open this Jamboard so you can move through the slides and go back if you need to. So electron configuration is a way of showing the structure of the electrons in an atom. So it's the way of showing the structure or the organization of electrons in an atom. And electrons are organized into kind of smaller and smaller groups, you might say. And we call those energy levels, sublevels, and orbitals. So an orbital, we're going to start with the smallest one here. An orbital is just a region of space around the nucleus where an electron is likely to be. So that's a definition that you should definitely commit to memory. Orbital. It's just a region of space where electrons are likely to be. Super important idea. And a single orbital can hold only 2 electrons. 2 electrons total. So that's kind of the smallest way that we organize electrons is into orbitals. And a single orbital can hold only 2 electrons. Okay, so that's the smallest. Now we're going to jump up to the biggest way of organizing electrons, which is in energy levels. And we've been talking about energy levels because we've been drawing our Bohr models and numbering our energy levels 1, 2, 3, 4, and so on and so forth, depending on how many rings our Bohr model has. So an energy level is just a ring in our Bohr model. And as you go further and further out from the nucleus, the electrons in that energy level gain energy. So the electrons in the energy level increase in energy. Increase in energy. Okay, and within an orbital, so now we're moving, we did the smallest organization, then the largest organization. So now we're moving to kind of the middle organizational level for electrons. Within an energy level, we have what we call subshells or sublevels. So I'm going to put sublevels / subshells, because we call them both. We use those words interchangeably, sublevels or subshells. And subshells are different shapes, or the different shapes or types of orbitals that we have within a particular energy level. And we can have multiple types, multiple orbitals of each subshell type. So we have 4 shapes of orbitals, 4 types of sublevels. We have the S sublevel, which is a spherical shape. Okay. Then we have the P sublevel, which we call a dumbbell shape, kind of like, you know, the weights you might lift at the gym, dumbbell. It kind of sort of looks like a weight you might lift at the gym. Maybe not exactly, but close enough. You see where they might get the idea that it looks like a dumbbell. Okay, and then the D sub level, the D shape or sub level, we say looks like a clover leaf. We say it looks like a clover leaf. A clover leaf. And then our fourth type of sublevel is called the S-type sublevel, but it's has all sorts of weird and crazy shapes, and they are very, very complicated to draw out. We don't really draw them. They're too complicated to draw by hand. The way that we look at what F sublevels look like is we use computer modeling, computer simulations to kind of simulate and predict what those shapes might look like. Does anyone have any questions on this slide? Okay, so let's kind of recap here before we move on. What is the smallest organizational level that we talk about when we are discussing electrons? What is the smallest organizational level? Type your answer into the chat. It only holds 2 electrons. What is the smallest organizational level that we have when we're talking about electrons? The smallest organizational level can only hold 2 electrons. What is that smallest organizational level? Okay, so everybody that I've seen so far is saying orbital, and that is exactly right. Orbital is our smallest organizational level. And then what is our largest organizational level? What is our largest organizational level? Go ahead and type your answer into the chat. What is our largest organizational level? Okay, so our largest organizational level is our energy level. So a ring in our Bohr model is our energy level. Okay, so we're just trying to apply this vocabulary here. All right, move to the next slide. Okay, so within a sublevel or a certain type shape of orbital, we can have multiple orbitals. Okay, and then within a certain energy level, we can have multiple types or sublevels of orbitals, multiple shapes of orbitals. And the variety increases as you go up in energy level. So in our table, we're going to be going down, but as the energy level increases, the variety of sublevels increases. Okay, so we're going to start out with energy level 1. In energy level 1, we can have just one type of sublevel. All we can have is an S-type sublevel. That's all we can have in energy level 1. It's pretty boring down in energy level 1. And I like to think of this as a hotel. So here's my Electron hotel down here. So down here in energy level 1, or on level 1 of our hotel, we can only have one type, and that would be the S-type room. We can only have one type of room, and that's the S-type room. Okay. Then when we go to energy level 2, we get a little bit more variety. We can have S-type sublevels, and we can have P-type sublevels. Okay, and so you see that in our hotel, we still have an S-type room, but now we also have some P-type rooms. Okay, then when we go to energy level 3, we add more variety to our shapes of our subshells or our shapes of our orbitals. We still can have S, we still can have P, but now we can have a third type of sublevel. We can have D-type sublevels. So you notice we still have our S, we still have our P rooms, but now we also have a new type. We have D-type sublevels or rooms. So you can see in our electron hotel, as we go up, as we use more energy to go up to higher energy levels, we increase the type or the variety of orbitals that we have. We increase the variety of the rooms as we go up in our hotel room. All right, so I'm going to number my floors down here. So 1, 2, 3. Okay, and then when we get to energy level 4, we can have 4 types of sublevels. We can have S, we can have P, we can have D, and we can have F. F. I'm having a hard time writing an F. Okay. All right. So the thing that's kind of interesting about these sublevels is that within an energy level, we can only have a certain number of each type of sublevel. So if we look at our hotel over here, in each energy level, we only have one S-type orbital. And that is the actual case when we're talking about organizing an electrons. We can only ever have one S-type energy or sublevel. And so in energy level 1, because we can only have S-type sublevels, and we can only have one S-type sublevel, we can only have one orbital. Okay. In energy level 2, we don't just have S-type orbitals. So we know we can have one S-type orbital, but now we have P-type orbitals too in energy level 2 of our hotel. And when we have P-type orbitals, we can have 3 P-type orbitals in one energy level. So one level can hold 3 P-type orbitals. So we have one S-type orbital, and now we also have 3 P-type orbitals for a total of 4 orbitals. Okay, any questions so far? All right, so let's move on to energy level 3. We can still have S and P orbitals, so we can have one S orbital, we can have 3 P orbitals, but in energy level 3, we now can also have D-type orbitals. And we can actually have 5 D-type orbitals. So we get 5 more orbitals in energy level 3. And then when we get to energy level 4, which I didn't draw in our electron hotel because it gets a little bit confusing or just becomes a lot of boxes to draw, we can still have one S orbital. We can still have 3 P orbitals. We can still have 5 D orbitals, and we get F orbitals now. So we can have 7 F orbitals. So if we add up this total, 7 plus 3 is 10, plus 5 plus 1 is 16 orbitals. If we add 1 plus 3 plus 5, we get 8 total orbitals. So our total number of orbitals, fill this in as 1 orbital, then 4 orbitals, then 8 orbitals in energy level 3, and then 16 orbitals in energy level 4. And we could keep going and going and going, but we don't need to go past the F level orbital. Okay, so how many electrons did we say an orbital can hold? How many electrons can one orbital hold? Type your answer into the chat. How many electrons can just one orbital hold? All right, yes, everybody who put 2 is correct. A single orbital can hold 2 electrons. So in energy level 1, if I can only have one orbital, and that one orbital can only hold 2 electrons, what's the maximum number of electrons that energy level 1 is going to be able to hold? Well, 1 times 2 gives me a maximum of energy level 1 holding 2 electrons. And that's why when we draw our Bohr model, our first energy level, we draw our nucleus, and then our first energy level can only hold 2 electrons. So any electrons past 2 have to go on further levels out. So if we were to draw, let's say, the Bohr model for beryllium, I switch colors for beryllium, Be. Beryllium is atomic number 4, so we know we have 4 protons and also 4 electrons in the neutral atom. 1, 2, and then that maxes out the first energy level. So we have to put electrons 3 and 4 in the second energy level because that first one's already filled with 2 electrons. And that goes back to the fact that we can only have an S or type orbital, and that we can only have one s orbital, and that one orbital can only hold 2 electrons. So it all goes back to this idea of electron organization. Okay, let's do energy level number 2. So in energy level 2, we said we have 4 total orbitals. So if we have 4 orbitals and they each can hold 2 electrons, how many total electrons can energy level 2 hold? How many total electrons can energy level 2 hold? Go ahead and type your answer into the chat. Well, 2 times 4, or 4 times 2, gives us 8 total electrons. So energy level 2 can hold 8 electrons. Oh, I totally did this math wrong here. This is a 9. I was wondering. 9 times 2 gives us 18 electrons in energy level 3. And then 16 times 2 gives us 32 electrons in energy level 4. Does anyone have questions so far? So these are numbers you should know. So repeat them to yourself. The total number of electrons that can be held in energy levels 1 through 4. 2, 8, 18, 32. 2, 8, 18, 32. You should be able to commit those numbers to memory, to say them off the top of your head. That is the maximum number of electrons that each of those energy levels can hold before it is totally and completely capped out. Any questions before we move on? All right, I'm going to move on to the next slide. So we said before, and I'm going to say it again, electrons in an atom are lazy. They don't want to do more work than they possibly have to. And so in our electron hotel, if an orbital is available down in energy level number 1, if a low energy orbital is available, they're not going to climb all the way up to a higher energy level. They want to use that the lowest barrier to entry energy level. So they're lazy. They're going to go into the lowest energy level or lowest energy state possible. So this would be lowest energy state possible because that's where they are the most stable. Okay, and everybody wants to be stable. They don't want to be unstable. That's why we see that light emitted as part of our flame test. It's because they can't maintain that high energy state that they jumped up into. They want to fall back down and go to where they are stable, where they have the least energy. So this principle, called the Aufbau or Aufbau principle, just says that same thing, is that an electron is going to occupy the lowest energy orbital that can receive it. So the fact of the matter is that the energy of the orbitals doesn't always go according to number, which is kind of counterintuitive because we call them energy levels. The order in which the orbitals fill from lowest energy to highest energy can be figured out by following this chart. So if we follow the arrows, the first orbital to fill would be the 1s orbital. The next orbital to fill would be the 2s orbital. And then the next orbital to fill after that would be the 2p orbital. And then the next orbital to fill after that would be the 3s orbital. And if we keep going, what are the next 2 orbitals that would fill after the 3s orbital? What are the next 2 orbitals that would fill? Go ahead and type your answer into the chat. What are the next 2 orbitals that would fill after the 3s orbital? So the next two orbitals that will fill after the 3s orbital are this 3p and 4s. So next we'd have 3p, and then we'd have 4s. Okay, and then if we keep going, then we'd go back around, and the next one to fill is this.
3D.
Anybody have a question? Okay. The next orbital to fill after that 4s orbital is going to be that 3d orbital. And so this is where it doesn't always go according to number, because the 4s orbital is actually lower in energy than the 3d orbital. So it doesn't always go according to number. So it's important that we follow this chart and we follow this pattern of filling. So after 3d, then the 4p orbital is the next lowest energy, and then 5s, and then 4D, and then we could keep going and going and going and going and going and list out all these orbitals, the energy level and the sub level. We could list them all out. We could keep going and going and going, but it just follows this pattern. Okay, anybody have questions on this? All right, I'm going to go ahead to the next slide then. Okay, so electron configuration is just how we keep track of where all the electrons are. So it's just a list of all of the orbitals that electrons are occupying for a certain atom. So this first blank is just electron configuration. Electron configuration is a list of all the orbitals occupied by electrons. And there's some certain parts of the electron configuration that we need to be familiar with. This number out front tells us the energy level. And sometimes we also call the energy level a shell. So it's a ring on the Bohr model, an energy level, otherwise called a shell. So that first number tells us the energy level. And what does the letter tell us? What does the letter tell us? Type your answer into the chat. What is that letter telling us? What is that letter telling us? Look back in your notes if you need to. That letter is telling us the sub-level or subshell. And the sub-level or subshell tells us the shape of the orbital. It's important to remember that that sublevel is telling us what shape the orbital is. So this S sublevel, what shape is the S sublevel? Look back in your notes and put your answer in the chat. What shape is that S sublevel? What shape is that S sublevel? All right, so everybody that's putting sphere, that is correct. The S sublevel is a spherical shape. Okay. All right, and then one last piece of our electron configuration is this number at the top. So this 2 right here is telling us how many electrons are occupying that particular part of our electron configuration. How many electrons are occupying the S sublevels of energy level 1. So this is our number of electrons. Okay, any questions about those pieces of our electron configuration? Are there any questions about that? Okay, so let's try example number 1 together. So if we look at this electron configuration right here, this 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. How many energy levels do we have here? How many total energy levels are there? Remember, the energy level is the number out front. How many total energy levels are there in this electron configuration? How many total energy levels are there? Go ahead and try it yourself and put your answer in the chat. So I'm seeing some different answers here. And I can see where we are getting these different answers. But what we're doing is all we're looking at is that first number, and we're just looking for the highest first number. So the highest energy level that I see here is this energy level number 4. And so that means that there are 4 total energy levels in this particular element's electron configuration. So if we were to draw a Bohr model, there would be 4 rings. So I'm going to draw that over here. I'm going to go ahead and draw our 4 rings. I'm sorry, my drawing's not super great. 3 and 4. Okay, so there's our Bohr model here. Okay, next what we want to figure out is how many total electrons there are. And we'll do this by looking at all the superscripts. So what we need to do is take all the superscripts. So we have this 2, 2, 6, 2, 6, 1. And we need to add all those up to figure out the total number of electrons that are in this particular configuration. So go ahead and do that. Add those up and figure out the total number of electrons and type that into the chat for me. So if you add up the total number of electrons, 2 plus 2 plus 6 plus 2 plus 6 plus 1, there are 19 total electrons. Whoops, got my wrong pin there. Let's go back one. Let's try that again. There are 19 total electrons, okay? So if we are going to put 19 electrons in our Bohr model, let's get a different color. We'll do that in a second. We're going to actually first figure out what element we have here, okay? If we have 19 electrons, and we're assuming this is neutral, it's not an ion, what element has 19 electrons in its neutral element? What element has 19 electrons? Type your answer into the chat. What element has 19 electrons? I'll give you a second to pull out a periodic table. Remember, for the neutral atom, the number of electrons is equal to the number of protons. So what element has 19 electrons? So if we pull out a periodic table, element number 19 is K, which stands for potassium. So this is element K, or element potassium. So just to recap, we can figure out the number of energy levels just by looking for the highest number in our electron configuration. And then we can figure out the number of electrons just by adding up all of the superscripts in our electron configuration. So we can find out a lot from this electron configuration thing. Does anybody have any questions before we move on? Okay, so let's go about trying to make a Bohr model from this information. So we know that potassium has 19 electrons, and we know that it's going to have 4 energy levels, so we put 4 rings. And I'm going to go ahead and put potassium in the middle instead of drawing all my protons and neutrons. So we have energy level 1, energy level 2, energy level 3, and energy level 4. Okay, so we're labeling those parts, and I would highly recommend drawing this Bohr model in your notes too, so you remember how to do this. Okay, so when we draw the Bohr model from an electron configuration, we just want to think about how many electrons are going to be on each energy level. So for energy level 1, we're going to look for all the pieces of our electron configuration that start with 1. And so the only one I see here is this first one, 1s2. And so the first energy level on my Bohr model is going to just have 2 electrons. So I'm going to draw 1, 2 electrons in that first energy level. All right, then we want to figure out how many electrons go in energy level 2. So I'm going to look at my electron configuration and find all the pieces of electron configuration that start with a 2. So I see this one, 2s2, and then 2p6. Are those 2p6 pieces of my electron configuration that have energy level 2. So if we add up the total number of electrons in energy level 2, 2 plus 6 gives me a total of 8. So in my energy level 2, I'm going to draw 1, 2, 3, 4, 5, 6, 7, and 8 electrons. Okay, any questions so far? All right, so go ahead and try it yourself. Figure out how many total electrons energy level 3 should have in it. So look at your electron configuration, find the pieces of the electron configuration that have energy level 3, and then add up the total number of electrons and put that total number of electrons for energy level 3 in the chat. All right, so if we look at this, and a lot of you already got this, we have 3s2 and 3p6. So those are our two pieces that are energy level 3. And if we add up the 2 plus the 6, that gives us 8 total electrons in energy level 3. So you can see over here, I've drawn 8 electrons, 2, 4, 6, 8 electrons in our energy level number 3. Okay, and then last but not least, energy level number 4 is going to be our easiest one to draw, because there's only one piece of our electron configuration that has a 4 out front. And so there's only one electron in energy level 4. Okay, and that's good because looking at your periodic table, so now take a look at your periodic table. How many valence electrons does potassium have? Remember, it's in group 1 of our periodic table. So how many valence electrons does potassium have? How many valence electrons does potassium have? Put your answer in the chat. And everybody who's putting 1, you are exactly right. Potassium's in group 1 of the periodic table, so we expect it to have 1 valence electron. So this means that we drew our model right, because in this valence shell, this outermost shell of our model, there's only 1 electron. There's 1 valence electron for potassium. So I'm going to label that valence electron. Okay. All right, so we did one example where we started with electron configuration. Now we want to go the other way. So let's try and write the electron configuration for vanadium, which is capital V. It's number 23 on your periodic table. Number 23 on your periodic table. Okay, so what we're going to do when we go the other way is we're going to use our chart. And all we're going to do is we're going to add in the numbers of electrons that go in each type of orbital. So the first orbital we'll write down is our 1s orbital. And that 1s orbital, we can only have one s orbital in each energy level, so it can only hold 2 electrons. So we're going to put the maximum number of electrons that we can in that 1s orbital. And then we're going to keep going. Once we filled that orbital, we're going to keep going. And the next thing we get to is our 2s orbital. So I'm going to write 2s. And because it's an s orbital, there can only be 1, and 1 orbital can only hold 2 electrons. So the maximum number of electrons is 2 again. So 2s2. It's filled up. So now I've used 4 of my 23 electrons, but I still need to fit 19 more in. So I'm going to keep writing out my orbitals. So I'm going to go around to the next one. So the next orbital is 2p. Okay. But p orbitals, we said, looking at our previous chart that we filled in, p orbitals, we can have 3 p orbitals. And those 3 p orbitals can each hold 2 electrons. So all the p orbitals put together can hold 2 times 3. So they can hold 6 total electrons. So in that 2p orbital, I'm not just going to put 2 electrons, I'm going to fill it all the way up with 6 electrons. Okay. And when I put those 6 electrons in, now I still have 13 more electrons that need spaces. So I'm going to keep going. And the next thing I hit is 3s. And we know an s orbital can only hold 2 electrons. So I'm going to put a 2. And that narrows me down. Now I need to fit 11 more electrons in. So I'm going to keep going, go all the way up and around. And now I get to 3p. So I'm going to put 3p. And I know that p orbitals can hold 6 total if we fill all the p orbitals. So I'm going to put a 6. And now 11 minus 6 gives me 5 more electrons that need spaces. So now we'll keep going. We get to 4s. So I'm going to write 4s. And we know our s orbitals can only hold 2 electrons each. So I'm going to put a 2 up there. And now I just have 3 electrons left that need spaces. So I'm going to keep going around.
Wouldn't 4s hold, because on the top problem it says 1 on it, the example 1.
Okay, but that's because we ran out of electrons. We'd already put 18 electrons in place. So this last orbital, there's only 1 electron left to go in it. Does that make sense?
Yeah.
Yeah. So we're going to do the same thing here. So now we've got to 3D. So next thing I'm going to write down is 3D. And if we go back and look at the number of electrons that d orbitals can hold, there are 5 d-type orbitals. So if we have 5 orbitals that can each hold 2 electrons, the d sublevel can hold a total of 10 electrons. So it could hold 10. We could have 3d10, but we don't have 10 electrons left here. We only have 3 left. So that d sublevel, which could hold 10 electrons, is only going to get the 3 that are left. Okay. Does anybody have questions on that? So that's our whole electron configuration for vanadium. We wrote out every bit of where those electrons were. Electrons 1 through 23. This is where all of them are.
How many electrons can F hold?
F can hold up to 14 electrons because we can have up to 7 F orbitals. Okay, any questions on this? Let's see what's on my next slide. Okay, let's go ahead and try these problems. We're going to fill in this first blank, and then before we go, because we only have about 10 minutes, we're going to try these problems. So this first blank, the electrons that occupy the highest energy level, those are just valence electrons. We know this word. We've been using this word for quite some time now. And I used the wrong marker, I'm sorry. These are our valence electrons. So potassium's highest energy level is which energy level? If we look back at potassium, which we did up here, what's potassium's highest energy level? Well, it's energy level 4. So that's its valence energy level. Potassium's highest energy level is energy level 4. And we said that it has 1 valence electron. And we can figure that out from our electron configuration, but we can also figure that out by looking at the periodic table. Okay, so I'm going to give you about 4 minutes to try writing the electron configuration for silicon and writing the electron configuration for vanadium. So go ahead and just do the electron configurations. And if you want to try the rest, you're welcome to do that as well, but we will talk about that together. You have till 1:45 to try this. All right, let's look at these together. So if we write out silicon's electron configuration, silicon has how many total electrons? That's the first thing we need to figure out, is how many total electrons does silicon have? And so if we look at the periodic table, silicon is element number 14. So that means silicon has 14 electrons total. So we need to start writing out our electron configuration from lowest energy orbital to highest energy level. And we'll fill those orbitals with electrons until we get to 14 total electrons. So the first orbital is 1s. And we know that can hold 2 electrons. Okay, so that takes care of the first 2. And then we go to 2s, and it can hold 2 electrons. So that takes care of the next 2. We've taken care of 4 electrons. Then we'll go to 2p. And we know the p orbital can hold 6 electrons. So now we've taken care of 10 of those 14 electrons. So we have 4 more to go. So we did 1s, 2s, 2p. The next orbital will be the 3s orbital, which can only hold 2. Okay, so we need another orbital. The next orbital would be the 3p orbital. And we know that 3p orbital could hold 6 electrons, but we only have 2 electrons left. So our electron configuration will end in 3p2, with that 3p orbital holding 2 electrons. And we can check that we've done this right simply by going and adding up all of the superscripts in our electron configuration. So if we add 2 plus 2 plus 6 plus 2 plus 2, that gives us 14. And we know that was the number of electrons that we wanted in our electron configuration. So we know we did this right. Now, the number of energy levels, we just are looking at the numbers out front, remember? So we have energy level 1, energy level 2, and energy level 3. So the total number of energy levels will be 3. And we know the total number of electrons is 14. We already figured that out. And then this last piece is the number of valence electrons. And so for the number of valence electrons, we could draw out our Bohr model, but we don't really need to in this case. All we need to do is look for energy level 3, and then look to see how many electrons are in these energy level 3. So if we look at everything in energy level 3, everything with a 3 out front, we can see that there are 2 electrons in the 3s and 2 electrons in the 3p for a total of 4 electrons in our valence energy level. So 4 electrons in energy level 3, which is our valence electrons. Does anyone have questions on that? All right, and I'm going to go through the next one, but this is vanadium, so we've already written out its electron configuration once. But we'll do it again just for the practice, because this is very repetitive. So if you can practice it enough, you'll be able to remember how to do it for your test. So vanadium, we said vanadium is element number 23, so it needs 23 electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, and then we only have 3 electrons left to go in that d orbital. So if we look at our number of energy levels here, we have energy level 1, energy level 2, energy level 3, and energy level 4. So even though the last piece of our electron configuration was 3D, the total number of energy levels is still 4. So we need to write 4 energy levels. We know that there are 23 total electrons. And then our number of valence electrons come from energy level number 4. So we're looking for our energy level number 4. Whoops, I didn't change the correct pen. Let's try that again. We're looking at energy level number 4 right here. There's only one thing with a 4 out front, and that s orbital only has 2 electrons. So our valence energy level has 2 electrons in it. Just these 2 electrons. So our valence energy level has 2 electrons. Does anyone have any questions? All right, guys, well, we are out of time for today. We will finish these